Hello world, welcome to my channel. I'm Bound to Be Cody. In this series of tutorials, I show you a feature of my game, and then I tell you how it's made. Today's video, a pure C# behavior tree system for turn-based AI. Let's get started. So here we are in October 2025 when this was recorded. And next month will mark 6 years that I have been working on a hobby project, a game, a 2D survival game called Day 345, set in 1820s America, the Rocky Mountains, during the time of the beaver trade. And in all this time, 6 years now, I've been working on this game, starting with Unity, and a couple of years ago moving over to Godot. And in all that time, I have not attempted to introduce any creatures into my game. There are no, there have been no creatures, and subsequently no AI for those creatures. This is something I've always wanted to do. I've always wanted to work on behavior tree, understanding how AI works, how to basically bring to life my NPCs, both fauna and human. And so I was really excited to get started on this, and I've been working on it for, well, several weeks. And I finally reached a point where I felt like I understood how behavior trees work and was ready to show you what I have been doing. So this video is going to be probably longer than my other show and tells, just because of the amount of content that has been put into the behavior tree system that I have. I want to dig into the design of it. I want you to understand how it's made, and the goal being to not only just document this, but also for the viewer to be able to take this and use it if you so choose to do so. So this is a pure C# behavior tree system, and I've got on this slide here for turn-based AI, but it could be, really for any game, 2D, 3D, real-time, turn-based. The concepts are the same. The implementation could be the same as well. So in this video, I want to break it up into 3 sections. I'm going to give a slide presentation first to cover basically how the system looks, the components that make up the system. Excuse me. And then I want to jump into Godot and actually run the game and show you this system in action. And then in the last part of this video, I want to jump into code and look at the system. I'll show you each class. I'll show you how everything is constructed and how everything fits together, and hopefully at the conclusion you'll have a good understanding of a behavior tree, what it is, how it works, and how you might be able to incorporate this into a game of your own if you're working on a game. So stay with me, and we're going to step in through these slides. A pure C# behavior tree. What does it look like? Well, let's define it first. What is a behavior tree? And I've tried to put together a definition here that encapsulates what my understanding is from research. Behavior tree is a hierarchical decision-making model, and what it does is it organizes logic into a system of nodes that represent all the desired inputs and decisions and outputs used to control non-player entities. So each node is its own action. It evaluates and returns a success or a fail or a running if it runs more than one game cycle or game turn. And there is, I said that it's hierarchical. It does have parent and child nodes. The parent nodes are, in this implementation, are sequences and selectors, and they determine how the execution or the flow of the behavior tree occurs. They make behavior trees make complex behaviors easy to design, visualize, and maintain by breaking them into modular, reusable pieces of functionality that work together to bring creatures and NPCs to life. And I'm excited to get into it. This is something, again, I've really wanted to do for a long time, and I finally have it, and so I'd like to share it with you. This is the system design. On the left, you have a collection of classes that make up the core behavior tree system itself. On the right, we have other classes that make up how I'm implementing them in my game. And I want to step through each one of the components on the left, and we'll see how it all ties together on the right. So let's start with the base class. The base class, it's an abstract class which holds properties and methods, and it references a couple of classes that are shared by all the derived classes. It has a name property, which is a string that allows the nodes to be named. That just makes the builder more intuitive. You'll see that in a little bit. It has an ID, an integer, that is used to create an identifier for each node in the tree so that we know one from the other. It also includes a manager, which is just a class that manages the execution of the tree. And then it also has an execute method that is implemented in all of the nodes to perform whatever that node's purpose is. And it returns a value. Each execute is going to return a value from a result enum. And there's only 3 possible results: a failure, a success, or running. The action class takes in a function, which is a reference to a method outside of the class. The function returns a result back to the manager. The class itself knows really nothing about what the function does. It just simply calls the function method delegate it receives, and it returns the result back to the manager. That's an action class, so it actually does something. Condition class takes in exactly the same way a function, which is a reference to a method outside the class. This paragraph is exactly the same as the previous slide. Well, what's different about them? What's different from a condition and action? How are they different? Well, they're different in how they're used. Actions change the agent. Actions do something to affect the agent, in this case, a creature or an NPC, in some meaningful way. Conditions are used to check for something before making that change. For example, if a rabbit is not hungry, then there's no point in eating. So the condition would be, is the rabbit hungry? And the action would be, okay, then let's go find some food and eat. It should always return, this condition node should always return either a success or a failure. It should never return a status of running. Composite class. Now, in my implementation, the composite class is just an intermediate abstract class that provides its derived classes with additional functionality that's not provided for in the base class. So in this system, the composite adds the ability to keep a collection of children. So sequence and selector both inherit from composite, and they have the ability to have children, whereas condition and action do not have children and cannot have children in this system. Sequence class. The sequence and selector, they are probably the most difficult to understand in this system. The sequence class is used to cycle through its child nodes in the current turn until one of those nodes fails, until it returns a failure. So it kind of mimics an AND operation in programming. So it'll do an A and B and C and D. So you can think of a sequence like a crafting recipe that requires ingredients. So you can't make something unless you have all of the ingredients. So each child is like checking for a specific ingredient. If all ingredients are found, it returns a success. You're able to make the item. If you do not have a specific ingredient required, then you don't make the item. And so the process ends. And that's what happens with a sequence node. The moment it cannot find an ingredient, the turn ends and it returns a fail. Now, contrasting that to a selector node, that class is used to cycle through its child nodes in the current turn until one succeeds. So it mimics an OR operation. So run A or B or C or D. So it's like a checklist of possible things to do for the turn. So it checks each child to see if it returns a success. And if it does, the turn ends. If it doesn't, it'll just keep going until it finds another child that returns a success. Or if all of the children do not return a success, it will return a fail. And that's the selector. So it's very important to understand the difference between the sequence and the selector. The sequence being an and the selector being an OR operation. Now the manager class, those are all of the classes that are used for the core behavior tree system. Now, how we're implementing that system is via the use of a manager class. The manager class holds the instance of the behavior tree for a creature or an NPC. It stores the ID of the current running node, if there is a current running node, the name given to that node, and which node is the root node in the tree. It also controls the creation of IDs for each of the nodes, ensuring that those IDs are unique. And for each turn of the game, the manager calls behave, or we call the manager.behave method, and that is how we trigger the behavior tree to run. And it will check what I call a danger interrupt to make sure that there's no danger nearby for the creature or the NPC. And if there is no danger, then it will go ahead and execute the selector, the root selector, which you'll see when we actually take a look at the behavior tree that we have for our example creature here, the jackrabbit, the Rocky Mountain jackrabbit. That is my first creature for the game. Now the builder class, it's a utility class. It's used to construct the manager's behavior tree. And this is where it really gets interesting in implementing this behavior tree system. I use a fluent design pattern, and if you don't know what that is, the fluent pattern in C# is a way of writing code that allows you to basically chain methods together. Each method returns the same object it's called on, and that basically allows you to chain those methods together. So if you take a look at these examples down below here, on the left we have a non-fluent style. So you instantiate a builder, and then you call the three methods on the builder, method A, method B, and method C. With the fluent style of C#, you instantiate the builder just like before, but you can then call builder dot method A, and then dot method B, and then dot method C. So you can chain the methods together. They run in exactly the same way. It just allows you to write the code a little differently. And in this context, the context of creating a behavior tree, the fluent style is an excellent pattern to use because it kind of allows you to lay out all the logic for the creature or the NPC in a way that is visually understandable, easy to follow, and easy to construct. The builder class utilizes for the child nodes. Remember, I said that composite nodes can have children. So I utilize a stack collection to manage the child nodes. Think of stacks as like a stack of something, like maybe like a stack of plates or something like that. where you add the first one, then you put another plate on top of it, you put another plate on top of that. So it's a stack. So when you take off the stack, you're taking it from the top all the way back down to the bottom. So it's a specific collection type in C#. And for my behavior tree, it works really well. And what it does is it manages the child nodes in the composite selector and sequences. The builder class also uses method names that have been chosen to maximize the benefit of the Fluent design. And again, you'll see that in a little bit. This will all kind of come together when we look at the code. So what I've done is instead of calling it selector, I've given it a name, consider. And sequences are known as check. Conditions are if, actions are then, end. It basically in the composite stack, it pops the stack, and you can Google. I won't go into exactly all the details of how stacks work. That'd be a good video to look up and watch if you're not familiar with that type of collection in C#. Build is a method that returns the root node. Add node, of course, takes a look at the stack and then adds a child to whatever the current composite node is, or adds just sets the root value, the root node. That's what the builder class does. The behavior class is the specialized class that holds the definition for a particular type of creature. So in my game, I'm going to have at least 2 rabbits. We're going to have the Rocky Mountain jackrabbit, and we're going to have the Rocky Mountain snowshoe hare. Now, both of those creatures, they are unique, but they're going to share the same behavior tree because they're both the same type of creature. So rather than creating a separate behavior tree for each one, I can basically say, hey, this is how a rabbit behaves, and we're going to use that behavior tree for both of those creature types. I can do the same with deer and elk, moose. They could probably all share the same behavior tree. Cats can share the same behavior tree, like the mountain lion or even the domesticated cat. I don't know. There's lots of ways you can use behavior trees, and of course, if we can reuse things, reuse code, that's all the better. Now, this class is instantiated in the creature's Godot scene, where the delegated action methods are implemented. You'll see that in a little bit. So that's the system. That's the overall design of the system. It's quite simplistic. It's not overly complicated. It's not very large. If you Google or get on YouTube and look up behavior trees, you will find many other types of nodes that are used. I may end up implementing other node types. I don't know yet because, like I said, I'm just getting into it, just kind of wrapping my head around how they work. But for now, these are the node types that I have, the classes that I have that represent the behavior that I want to implement and I want to mock up. And everything's working well with these nodes. So we'll see what happens as we move forward. All right, so I'm in my game and I have spawned 5 or 6 rabbits, and I'm just going to kind of, this is a turn-based game, so nothing is happening right now. Everything is kind of suspended while the player is still, but then when the player moves, everything else moves. So I'm just going to move forward a little bit, get my cursor here, move forward a little bit, and we're going to watch. Now, these guys are all eating right now. They do spawn in with random levels of hunger and thirst preset, and so they're going to be hungry at different times. They're going to be thirsty at different times. So we'll see this guy here. He just finished eating a little tuft of grass, and now he's going to locate some water. If we look here on my region map, we can see we've got some water to the east here, and that's where he's headed. He's headed east to see if he can get him some water. So I'm going to move forward a little bit so I can kind of watch these guys. They're all getting thirsty. They all want some water. So they're going to come down here and try to find some water. You'll notice they're kind of congregating. And I'm just going to hit the space bar, so I'm not going anywhere. I just want to watch this. So they're congregating. They found themselves 2 or 3 tiles of water, and now they're drinking. In my current implementation, they don't really mind sharing water spots, water sources, tiles. They will congregate on a tile and drink together. But then when they look for food, they will go and find their own grass. So they will avoid grass that's being eaten by another rabbit. And I can do the same with the water, which is the beauty of behavior trees. You can pretty much code them to do whatever the behavior, is at your fingertips. You just figure out what you want to do, how you want your creature to behave, and then code that, and the behavior tree will run and they will make their decisions based on what you have coded. So I'm just going to I'll come back over here because I know they're going to be heading back to the plain area here as they roam around, and I want you to be able to see this. So I'm just going to kind of hit the space bar. So you can see their states. I've added some labels at the top to above each rabbit. These symbols down below speak to some of the properties of the rabbit. I will probably do a video on that feature later, but that will be a way that I will allow the player to kind of get some insight into what the creature's thinking, the state of the creature, things like that. So they're roaming around and they're drinking. Now I implemented now that right there is a bug. I don't know where that guy thinks he's going. There is nothing down there. So this is actually comical. I like this. So evidently I have not added in their behavior tree the limits of my region. And so this is completely unexpected. This is the first time I've seen this right here doing the video. I see how, oh, wait a minute, I need to limit their movement. They should not be leaving this region. If I left this region, if I went south right now, I'd jump to the next region. These guys are out in La La Land. They're not even in the game world in that sense. But this is one of the fascinating things about creating a behavior tree. Things happen and you look at it and you're like, wow, wait a minute, what's going on with this? Well, you didn't tell them they couldn't go there, so they're going there. So this is terrific. This is very, very fun to watch the behavior tree that you code come to life, animate your creature, and then, through observation, you discover where you need to, put on the brakes and say, wait a minute, we need to add some conditions here for these rabbits to make sure that they don't run off out of the game world, so to speak. All right, so that kind of shows you how they're working. They're locating food. Fortunately, the food is not off the map, so when they get hungry, they're definitely going to come back. But I'm going to need to add a condition check in my behavior tree to make sure they don't leave the region, and that's great. That's just great. So I'm enjoying working on this. You can see how enjoyable this might be, to watch these creatures come to life and start doing things, good things, not so good things. But anyway, so this is how it's working. I now want to take you into code, and let's look at the behavior tree for the rabbit. This is the first creature in my game, day 345, A Struggle to Survive. These are fun times. All right, let's jump into some code. All right, we are in my game's code. We're looking at the base class in the behavior tree. Not much to it. It's pretty simple. This class will have all of the properties, that the other classes are going to inherit. Not much to this. The constructor takes in a name, and the manager, which I call tree, assigns that. And of course, we've got this abstract execute method that's going to get implemented in the other classes. So this is an abstract class, meaning that we're not going to instantiate this. We're not going to create an instance of this. This is just going to have properties and methods that will be used elsewhere. So that's the base class. Not much to it. Moving along, let's take a look at the action class. So here's the action class. Basically, it has a function which returns a result, and we have the execute method that it implements. And so, again, not much to it. We are inheriting from our base class and pulling in what we need to execute the method. So very, very simple code at this point. Let's look at the condition. Looks almost the same. And in fact, it is the same except for the naming of the property. But it does the same thing. It basically takes in a function which is given to it, and then executes that function, and then it returns the result back to the manager. So again, very simple code here. Let's look at the composite. This is where things get a little interesting. We have a list of children. Remember, the composite provides the ability to have a list of children, and so we can see how we have this list of children, and we have this method here to add a child to the list. Again, pretty simple, right? Let's take a look at the two classes that inherit from the composite, and that would be the selector and the sequence. And again, as we move up in the classes, we get a little bit more functionality. It gets a little bit more interesting. So we have an integer property to manage the current child index for this particular selector, and we take in the manager and a name, and we have this execute method here. Remember, all of them will implement the base execute, all of the nodes, and so the base execute implementation of the base execute abstract method here for the selector, this is where things get a little more interesting. So keep in mind that the selector is an OR operation, okay? And so while the current child index is less than the number of children, so we're going to loop through, we're going to get the child, we are going to go ahead and execute the child node, and we're going to get back a result to this parent node. Now, if the result is running, then if the current running ID is null, then we're going to set the current running ID to the child's ID. We're going to set the name of the node. That name property is what appears above the creature in my game, and it's just for that purpose. I've got it there just so that I can see what's going on. And it's just going to return back to the manager that it's still running. Otherwise, if it is a success, then it's going to reset the children, return a success. Otherwise, it'll increment and hit the next node, and it'll just loop through until it reaches the end. Then it'll reset, and then it'll return a failure. The reset child just simply changes the current child index to 0 and the current running ID to null, so since there's no child node that's actually running. So again, the selector, it runs its children until the first one succeeds. And when we hit a success, it's going to return. And otherwise, if it's a fail, it'll just keep going. Okay? So that's what the selector looks like. Not much to it, more than the action and the condition. But again, these are very succinct classes. They do what they do very well, and they do one thing well. That's a good principle in software design, that your classes do one thing well. Let's look at the sequence. Sequence looks similar, but functions, again, different. The sequence is an AND operation, so it runs its children until the first one fails. So you can see that while we have our while loop here, again instantiating a child, returning or executing the child's execute method. And if it's running, we're going to do the same thing. We're going to set the current running ID to the child's ID. We're going to set the name to match the child's name. We're going to return back to the manager a running. Otherwise, if there is a failure, and remember this in a sequence, like a recipe, you need all the ingredients in order to be successful. And so if any one of these children fail, it's going to return a fail. Otherwise, if it's a success, then it will return a success. And again, the reset child private method here just simply resets the index back to 0. And the current running ID, it sets that to null. Now we do have this BT result, which is behavior tree result enum. And that guy it's just an enum that returns either a fail, a success, or a running, and all of the nodes return one of those three values. So that is, I think I covered everything of the base and the action, the condition, the selector, the sequence, and the result. So these 6 or 7 classes here form the core of the behavior tree itself. All right, let's locate the rest of this feature. I want to take a look at, let's look at the manager real quick. So the manager has a counter. It keeps track of the current running ID, the current running name of the node that's running. It has a root node that gets assigned when the builder builds the tree. It has this read-only function that returns a result called the danger interrupt, and I'll explain what that is. But in the constructor, we're basically bringing in the manager and basically a danger interrupt. So what happens here, and I've got some comments in so that you don't have to hear me give all the nitty-gritty details. You can read these comments yourself. But basically we have a method here to get the next ID. This is important. I'm using interlock in system threading to make sure that the next ID that is generated is unique to this instance of this manager. And that's what that does. The behave method is the method that is called from the node, from the scene node, the Godot scene node, to actually make this tree execute and run. So I just called it behave. And if the root node is null, then it will return a fail, meaning that there is no node to work with. And then we have what I call the danger interrupt. Now, what the danger interrupt is basically it gives me the ability to, regardless of where the behavior tree currently is in the turn, regardless of what's happening with the behavior tree for a particular creature. This allows us to basically run a check to say, okay, let's say, for example, the creature's eating or drinking, and a predator approaches. We don't want the rabbit to sit there and drink until he's full before he decides to run away from the predator. So the danger interrupt is going to be a method that I call to say, hey, do we have any enemies around? Do we have any dangers that I need to stop what I'm doing and react to? And that's what the danger interrupt is for. So if there is danger, then we're going to basically set the current running ID and the running name to null. We're going to say, hey, stop doing that. We don't want to do that. We want to do something else. Otherwise, it will just execute the root node, which is whatever that node, whatever the current node happens to be. And that's what we have with the behave. Anything else I need to mention with this? I don't think so. But you can pause the video and kind of read these notes. All right, so that's the BT manager. Let's look at the BT builder. This is kind of interesting. The builder. This is my Fluent builder, and it is a utility method. A utility class, and its purpose is to build the tree, build the behavior tree. And so here's where we have our stack collection of children for the node. If it happens to be a composite node, we have a reference to the BT, to the manager class. We also have the root node being tracked here. We take in that manager, and then what we're doing here is we are implementing all of the behavior tree classes that we looked at earlier. So that whole list of classes that make up the behavior tree, the base and the action and the condition and the composites, the selector and the sequence. This is where we're actually implementing them, and we're actually calling them. Now I give them different names, and you'll when we look at the next class, you'll see why I chose these names to make it more readable. But just kind of giving you an understanding of what these classes are doing. So when our constructor, we're basically assigning the manager. The consider method, these, keep in mind, this is the Fluent pattern, so it's going to be returning itself like we spoke about in the slides. But what this does is this generates a new selector, adds the node to the tree, and then pushes it onto the stack. The check method generates a new sequence. Same thing, pushing it to the stack after it creates the node. The if method is implementing the condition. So we're going to create a new condition node and adding that node to the tree and returning it back so that we can chain these together. The then method implements the action. So if condition is good, we're going to implement the action. Again, does the same thing. It returns back to the caller so that we can chain these all together. The end is a way to basically end a composite node. So as we're adding in the behavior tree, when we're constructing the tree, we're going to be adding nodes. And if we are inside of a composite node, then those nodes, of course, are going to be child nodes that are going to be added to the stack. What this does, the end actually pops the stack. It basically backs out of the stack so that we can then add another sibling to the parent list. The build, simply we do some checks for to make sure that the tree is constructed correctly, and then we return the root node. And then we have the add node method where we're actually adding nodes to the tree. And I want to make sure that you see all of the code. So I'm just going to kind of slide up here. Make sure that you can stop the video or pause it. And yeah, I've got everything listed. Okay, so that's the builder. And now we're going to take a look at the actual behavior that's going to instantiate the manager and actually use the builder. Now here's where this class is where it all comes together. This is where all the pieces are put together in the puzzle to see exactly what's going on. So we have this hare behavior, and I'm going to, in my behaviors here, we're going to have, you know, a hare behavior and a deer behavior, and every creature in the game is going to have, every type of creature is going to have its own behavior. And this is where I can tailor the behavior trees to the specific creatures. So these can all be different. Or they could share functionality depending on, you know, what I want. I'm imagining eventually I'm going to have a collection of probably, you know, 40 or 50 different behaviors that I want to implement for these nodes, and it's going to be, you know, hopefully a system that I can, when I introduce a new creature to the game, I can basically use the behavior tree to build it and get it all like I want it and give it the behavior that I want it to have. So here in the constructor, we're going to take in a dictionary of delegates. Yes, we can have in C#, we can have a dictionary that actually holds delegates, which are references to methods elsewhere. And these are the actions that we're going to be basically passing into this behavior tree. So we instantiate a new manager, and with the manager, we're going to add a tree to the manager. So here's our Fluent implementation. And this is where you can see the beauty of using a Fluent pattern. And I've added the string names so that we can just have an understanding of how these, you know, what's going on in the tree. This is just, these names here, these string values are just to help to understand what the steps are and how these steps are implemented. So the consider, this is the first node, and so in this consider, we're going to be checking for some things. So we're going to consider, this is our checklist, and we're going to go down through, and the first thing we're going to do, we're going to check for health, and if we're going to check for injuries here, and we're going to run the function action that's named injured, and these are coming in from the delegate dictionary. Okay, these actions here. So you see the action, and we're implementing that action. So we're going to check, and if the rabbit is injured, then we're going to locate a shelter, and then we're going to rest. So this is the behavior that I want. Next, we're going to check for thirst. If thirsty, then locate water, and then drink. If hungry, locate food, and then eat. And then there's going to be some instincts. This is a separate list of to-dos, list of things that need to be done. We're going to check for whether or not it's curious, and if it is, then we're going to run the isCurious delegate method, which I'll show you where that is in a minute. And if it's curious, then it's going to be alert. If it is roaming, then it wants to roam, and if it wants to roam, then we're going to let it roam. So you can see so far these are the implemented behaviors. You'll notice that there's nothing in here about checking for dangers or running away from players or the player character or NPCs or predators. When I get to that point in my behavior tree, then I'm going to add some checks and some considerations for those behaviors. And I'll basically add them to this behavior tree. So there's the danger interrupt that's getting passed in, and which is another action, another function delegate called danger nearby. All right, so this is my behavior tree for a hare or a rabbit. All right, so where do we implement this? Well, that would be in the scene node itself, the rabbit or jackrabbit scene node. So if I go down here, my nodes, fauna, jackrabbit's the first fauna in my game, so here he is. This is the actual code behind for the jackrabbit scene in Godot. Let's go up to the top here and take a look. And I always in my nodes, my code behind for my Godot scenes, I always have an initialize method. Of course, we've got the ready method, which is overridden. This is the base ready method for the Godot scene node. So that's going to run, but then the next thing that happens is it's going to, I call this initialize. This isn't something that's built into Godot. This is just a common method name that I use when I'm initializing nodes in my game. So in the initialize, I will pass in the fauna instance, which is basically all the properties of a specific fauna in my game. I kind of break down my different objects in the game to definitions and instances. Definitions being static data that doesn't change. Those are loaded into JSON dictionaries. The instances are also loaded into a separate dictionary, but the instances contain the changeable properties of a particular thing. And so in this case, I'm bringing in my fauna instance. I'm also assigning the definition for this fauna, the scene ID, so that I can track the scene and search for it in my scene tree in Godot. Here's where I am defining my dictionary of delegates. Okay, so this is where it all kind of comes together. So I have my hare actions, which is a new dictionary of delegates. So these are all methods that are implemented in this class, in this code behind to my Godot scene. So these are the string values that are assigned to the dictionary. So we've got, a key value pair. So the keys, these are all the keys, and the delegates are the values. So for example, danger nearby is a method. It is a method in this class, and I'm going to pass a delegate or a reference to this method into my behavior tree. And this is how it's done. So if I control click, jump down, so this is going to return a result, a BT result, which is my enum. And danger nearby currently doesn't do anything. I just return a fail so that it can jump to the next one. Injured is the same way. And so going back up here, I basically in my code behind, I created all these methods, and I'm setting this dictionary of delegates for these methods, creating that, and then I'm going to pause so that my clock can finish its thing. I'll be right back. All right, so the Westminster chime on my clock is done. Didn't want that to affect my narrative here. So anyway, we're instantiating this dictionary of delegates, these methods being defined here in the code behind of the scene. And then we're going to instantiate a new hare behavior. We're going to pass in that dictionary, and that is how we're able to call the dictionary records inside of the behavior tree when it's created. So this is really cool to be able to actually have a dictionary of delegates that point to methods somewhere else. That's pretty cool. All right, so I'll show you real quick that all of those methods that are passed in to the behavior tree what I ended up doing with this is stubbing these out so that my fauna engine, which is a singleton, it's only going to get instantiated, the fauna engine is only going to get instantiated one time. Now, there might be in a scene, in a particular scene, there might be 20 or 30 fauna in the game of different creatures, different types, things like that. So I want to keep the code behind of the scene very lean as possible. All right. Because even though Godot, I understand, does optimize scene instances such that the methods are not duplicated in memory, but all of the properties of the scene is. Regardless, in principle, I want to keep these lean. I want to keep my scene tree in Godot very lean. And so what I decided to do was implement all of the methods, these delegated methods, over in the various singletons that I have. Mainly for this is the fauna engine, but I've got some others. World engine I'm using to get random values to return whether or not the creature is curious or not, things like that. So these are all methods. I will show you some of these, kind of give you an idea how to code the behaviors. But you can see here that they're basically methods that call into another class, and pass in the instance of the creature and returns back a BT result, a result of success, fail, or running. How do we actually in each turn call into the tree and make it do what it needs to do? Well, that is answered in this update creature state. And update creature state is handled in the process node. Process method. So what I'm doing here is the way I'm allowing this to only work, because process is going to run at the speed of the game, right? And so in order to control how often this method gets called, I have a world clock, and so I in a variable here, a property here in this class called last world clock. So I set the last world clock based on the whatever the world clock is, and then if they don't match, that means that the player has initiated a turn. And so when the player initiates a turn, we're going to set the last world clock to match whatever the current world clock is. Then we're going to call update creature state. And this is where I am controlling what image I'm displaying for the state of the creature. And I'm also, very importantly, I'm calling that behavior manager behave method. And so right here, this is where I'm getting the status back from the behavior tree. So we're going to go ahead and call a behave method of the behavior manager, and we're going to, for each turn, we're going to, consume some or increase the hunger level of the creature. We're going to increase the thirst level of the creature. And then we're going to do some, after the behavior is done, we're going to do some checks. I don't like how beefy this is. I really want to trim this down. I need to refactor this because I don't like seeing all this code in a node that's in the scene tree for Godot. So I'm going to probably refactor this. As much of this that can be refactored and pushed into my singleton classes, I'm definitely going to do that. I just haven't done that yet. But just to kind of give you an idea of what I'm doing here to process my actions that have happened in the behavior for the creature. So here's I'm currently working on the ability to capture or catch rabbits. So I've got a new structure that I've created that's basically a cage or a trap that traps the creature alive. And so what this is doing is basically saying, hey, the hare just moved. So let's see if he lands on on one of these traps, and if he does, then we're going to trap the creature. And that's all this is. This really isn't anything particular to the behavior tree, so I won't really get into what's going on with this, but anyway, the idea here is that I'm just adding a check here after the animal moves. This is probably where I will be, no, I was getting ready to say this is probably where I will check for whether or not the creature runs off the map or not, but actually this wouldn't be the place to do it. It would be in the roam method. I will check for that and make sure that he doesn't roam off the map, and that's where I'll do that. So we'll take care of that in the Fauna engine itself. So anyway, yeah, this is basically how I'm doing the method delegates. So let's take a look at a couple of these, and we'll see how I'm actually implementing the brain work of the behavior tree itself. All right, so when we look at these methods, keep in mind that, my code is going to be different. Up to this point, I think a lot of what I've showed you, you could actually, copy and use, write it out, and certainly the behavior tree itself. I've given you all the code you need to implement a behavior tree using a fluent pattern. Now that we're into my implementation, this is where it's going to deviate. You may not have a fauna singleton or things like that, so just keep that in mind. But I do want to show you how I'm implementing. I'm just trying to mentally think here. What do I want to basically cover first? These don't really do anything right now. They're stubbed out. Bored, wanting to roam is curious. Okay, well, this one here, the is curious, I simply just get a random number. So 50% chance that the fauna is going to be, the rabbit's going to be curious. So we're going to return a success if the value is 1. Otherwise, we're going to return a fail. So that's the is curious. The be alert is a method in my fauna engine. I'm not really sure what I'm doing there. Let me take a look here. So for be alert, for this behavior, I get the fauna instance from my database singleton. So I go into my fauna instance dictionary, selecting the record from based on the ID, and then okay. So here, what I'm doing is I'm just setting the movement state to stationary, and the visual state. This is this particular sprite that I'm using, alert, and I'm returning a success. So be alert is just simply changing the state of the creature and its sprite. That's really all that's doing, and then it's just returning a success. So maybe in the future I would add to be alert. Or maybe I would create another method to do something more than just change the condition, or the state of the creature and the visual representation in the game, the sprite. But that's all that's doing at this time. Let's look at something a little bit more interesting. How about is hungry? Let's look at that. So I'll jump over to my fauna engine, my is hungry method. All right, a little bit more going on with is hungry. So we've got, we get our instance, we get our definition, and then we're going to return a result. And so if the fauna instance is not equal to null and the fauna instance hunger level is greater than or equal to max hunger, then I'm going to return a success. Otherwise, I'm going to return a fail. So we're basically checking to see if max hunger has been reached. And if it has, then we're going to say, hey, this guy's hungry. Otherwise, we're going to return a fail and say, nope, it's not hungry yet. And since I'm here in the engine and I've got these methods, the implementations of my delegates, I'll just stay right here for a second. Here's locate grass. So if he's hungry, what's going to happen? He's going to locate some grass. So how do we do that? So I get the instance, I get the definition from my dictionary. I'm basically checking food location. So this method basically locates the nearest grass tile in the region that I'm currently in. And all that is just another method that does some wizardry to figure out, looking at the flora dictionary, pulling based on the definition for the types of flora that are grass, which in my case is key 3 and key 12. And then basically if it contains the key, then we're going to basically look for the nearest tile. And there's a for each here in my dictionary to determine where the nearest tile is. And yeah, just some more, more logic, more code. And then it'll return back whatever that nearest tile is. If we hit the back, then if the location returns a valid location, in other words, we do have some grass somewhere that this creature can eat, then we're going to set the location property of the instance to the food location. We're going to set the movement state to stationary, the visual state to feed, and return back a success. So once we find, we locate the grass, and keep in mind this will take several turns. So in the case of the locating of the grass, we're going to return two possible states. Either we found the grass, so the location of the fauna matches the food location, so we have found it, so now we're going to set the state to feed so that it can return success in the tree. Otherwise, we're going to still be looking, so we're basically setting the destination to equal whatever the food location was up here, and we're changing movement state, we're setting visual state, we're setting the location. Again, just some methods that do things, moving towards that location, and on move, we're triggering, that's an event, we are triggering the movement request so that we can actually move the creature in the game, and then and otherwise, if there is no food, then it'll return back a fail. So this is the implementations of those delegate methods. And then, of course, eating grass does similar. We get the instance, we get the bite size of the rabbit from the fauna dictionary, and if the hunger level is less than or equal to 0, then the rabbit is full, and so we're going to remove the grass from the world, and it just goes through the process of doing that. By the way, this is how I'm able to locate the scene, the specific piece of grass in my scene here, by instancing the Godot object from the scene tree, passing in the scene ID. So I store the scene ID in my flora, and then queue-free this node gets rid of it. Otherwise, we are getting the flora instance, and we are removing, instantiating, and queuing. So this just is the reason I have this if and else here, is because in my game, keep in mind that what I mentioned earlier about the scene tree and keeping it lean. My trees, my flora instances contain a lot of properties. Okay, pine trees have pine cones, and there's bark, and there's cuttings that you can take, saplings that all kinds of properties to flora, and branches and things like that. And so when I create my region, I spawn in flora shell objects, which are lean versions of the trees, and then they only have just a few properties, just like the type of tree and the sprite for the tree, and that's basically about it. Maybe the age. I can't remember now. It's been a long time since I worked on that engine. But anyway, but then when the player walks up to a tree and clicks on it, well, that converts that flora from a shell object to an instance object, and that's where we assign all the properties, the random properties of those flora. And of course, the player knows nothing about this. The player, sees a bunch of trees. It doesn't know that they're all shells. They're empty except for the ones that he clicks on. And when he clicks on it, that's when it becomes a more beefy Flora instance. And that's how you can make your game faster, by doing tricks like that, things like that keep your scene tree nice and lean. So, if the rabbit walks up to a Flora shell, then I need to convert it to a scene, because the Flora shell doesn't have food content in it. Otherwise, it hits an instance, it already has it, so then it just queue frees it, So anyway, this is just a little more of the code on how this is working. And so we just basically reduce the hunger level per turn and we keep it running until the rabbit's full. And when the rabbit's full, then we say, hey, we're full, we're done. All right, so that's eat grass. Rest, you can see how I've implemented rest. I'm not going to bore you with the details. Locate thickets. So rabbits, and this is not actually something I've implemented yet. So I've written this method, but I haven't actually built it into the tree yet to check for this. But when a rabbit is injured, they're going to try to locate shelter. So there's thickets throughout the game. The region will have some thickets in forested areas, and they will try to find one of those thickets and run to that thicket. When it gets to the thicket, it will stop and it will rest. And this is all chaining of methods in the behavior tree to tell it what to do. Okay, hey, if you're injured, then locate a shelter. And when you find that shelter, then rest so that you can rebuild your health. And this is how we can chain these things together. So yeah, I'm trying to think, is there anything else I need to explain? I think I've pretty much covered it. Yeah, I think so. I think we're at a stopping point here. I've covered the classes for the behavior tree system itself. I've shown you how I have implemented it, how I've created a manager that, how we have a fluent design pattern for creating the tree and allowing us to pass in method delegates into a dictionary that's passed into the tree, the scene tree, so that it can then call back out to those delegates and return results back to the manager of the tree. I've shown you how I have considered, the Godot scene node itself for the hare, for the rabbit, the jackrabbit, and how I'm keeping it lean. I'm using a singleton to actually hold the content of the methods. Again, even though I'm pretty sure I've read that Godot does a good job of not duplicating code when it instances the nodes in the tree, in the Godot tree, scene tree. But still, in practice, I want to keep this as lean as possible. Yeah. What do you think? I'm really excited about behavior trees. I've enjoyed learning about them. I've enjoyed putting this together. I am looking forward to building it out, making it, more extensible, and maybe I will introduce some different types of nodes as we go forward. But for now, I think I have what I need to move forward in my implementation. I'm going to wind down this video, and I really hope that you gained something, you learned something from this. I hope it was beneficial. If it was, if you'd like to see more videos like this, then consider subscribing to this channel. I pretty much only create Godot videos using C#, demonstrating what I'm doing in my game, Day 345, A Struggle to Survive. If you'd like to subscribe, please do so. And if you found this video helpful, then please consider giving me a thumbs up. I sure would appreciate it. Until next time, I'm bound to be coding.